Please believe me when I say, I love my job. I get to do the one thing I love more than anything else, learn, and help other people learn at the same time. It's a win-win. But there are times when my job begins to feel alarmingly like traditional work, as when, say, the vagaries of time suddenly conflict with the artificial deadlines I have masochistically imposed upon myself. October is already my hardest month, given the increasingly difficult obligation of a Halloween episode. And what should happen this October? But yet another sickening slump in the seesawing story of our second closest solitary star. I like my video on Barnard Star. It's one of my most popular, and, I think, still largely informative. So what if it spends a fifth of its runtime speculating on the geology, climate, and putative biosphere of a planet that doesn't exist? Planets of its type, whether around Barnard Star or not, have been speculated about in science papers for years, and there's still no reason to assume that Barnard Star doesn't have one. For those who missed my first You Are Here video, here's the recap. In 2018, a paper published in Nature by Ignacy Ribas and colleagues purported the existence of a super-Earth-sized planet around Barnard Star. Examining 771 spectrographs of the star taken over the course of 20 years, they unearthed what they assumed to be a consistent radial velocity shift of 233 days, which would indicate a planet of about 3.2 Earth masses at around 4 AU, or about the orbit of Mercury, from its star. Such a planet would have a climate and geology similar to Saturn's moon Titan, which led me down a rabbit hole of wild visions of what form of life might thrive there. The team claimed in the press that there was, and I quote, a 99% certainty of this planet's existence, a pledge I took enough to heart to make the discovery of Barnard Star B my top astronomical event of the year. I have since learned, however, that 99% certainty, or as scientists call it, 3 sigma, is not considered fair odds when it comes to announcing a discovery. And, sure enough, in 2021, a team in Texas employing the Habitable Zone Planet Finder checked their results and found that what the previous team had assumed was a continuous signal was in fact transitory stellar activity, and only appeared continuous because it just happened to appear during the 771 shots the team took. I refuse to take a pie in the face for this one. Peter van de Kamp, the head of Sproul Observatory until 1972, insisted for decades that Barnard Star had a planet, before it was revealed to be a faulty telescope. Barnard Star, in other words, has form. And this week, when yet another planet was announced to be in orbit around it, I wasn't about to jump on the bandwagon until I saw a number higher than 99%. I didn't, but, on the word of someone I trust, decided to go forward with this anyway. So, in full acknowledgement of how bitter my words will taste once I eat them in a few years' time, I introduce to you Barnard Star B. Again. Barnard Star B II was announced in the journal Astronomy and Astrophysics on the 1st of October 2024 by a team led by the Spanish astronomer Yonai González Hernández, employing the European Southern Observatory's Espresso machine, that is, the Echelle spectrograph for rocky exoplanets and stable spectroscopic observations. Espresso is designed to locate extrasolar planets by radial velocity, the tried-and-true workhorse of exoplanet studies that found the first exoplanet around a Sun-like star in 1995, and which had supposedly detected the previous Barnard Star B in 2018. Radial velocity does not observe a planet directly. Rather, it examines the spectrograph, or rainbow produced by the diffraction of a star's light, for the minute shifts from red to blue caused by the forwards and backwards motion of a star as its planet tugs on it. After observing 157 spectrographs over the course of 4 years, and running them through a statistical filter, the team believe they have identified a candidate planet with an orbital period of 3.15 days. Unfortunately, Barnard Star B version 2 is nowhere near as inspiring as its phantasmic predecessor. It has been somewhat demeaningly dubbed a sub-Earth, because its mass, at 0.37 Earth masses, makes it about 3 times the mass of Mars. Its distance from its star, 0.023 AU, gives it a surface temperature of about 400 K, comparable to that of Mercury. And chances are Mr. B resembles Mercury in other ways as well. An airless, cratered hunk of metal and rock. That said, we don't know its surface gravity. Radial velocity lets us know a planet's mass, but not its size. If we grant Barnard B an equivalent density to the densest planet in our solar system, which happens to be Earth, then it would possess an escape velocity approaching 8 kilometers per second, high enough to retain an atmosphere of nitrogen, oxygen, and possibly even water, though its proximity to Barnard's stellar activity would almost certainly mean that, without an exceptionally strong magnetic field, any atmosphere would be all but totally stripped off. If a signal identified in 771 shots can be deemed bogus, I am somewhat wary of a signal derived from 157 shots. But as a non-scientist, I must trust in their calculations, just as I did last time. Along with the most certain planet, the team also identified 3 other potential candidates, all very similar to the main attraction. An interior planet of 0.22 Earth masses, and 2 superior planets of 0.31 and 0.17 Earth masses respectively, which would mean the latter planet was roughly the mass of Mars. Sadly, none of these planets come close to Barnard Star's habitable zone, and likely also resemble Venus or Mercury. Barnard Star's habitable zone lies at around 1/10 of an AU from its russet surface, and there is no reason to assume a planet cannot still be hiding there, yet to be found. With an estimated age of 12 billion years, any planet around Barnard Star would have far longer for complex life to evolve. The ultimate goal of the Espresso project is to locate an Earth-like planet, which, so far, it has not achieved. But other projects aim to surpass it. The Terra hunting experiment, set to begin in 2025, is described on its website as the most intensive search ever attempted for Earth-like planets around the nearest Sun-like stars. Run by Dieter Queloz, one of the first to confirm the existence of an extrasolar planet, it will utilize the HARPS 3 automated spectrograph, soon to be installed on the Isaac Newton telescope in La Palma, to scan nearby stars for a decade. The Amazo Nez High Dispersion Echelle Spectrograph, or ANDES, to be installed in the extremely large telescope in Chile, will scour the atmospheres of exoplanets for potential biomarkers. As you can probably tell, I am not good at predictions, but I do feel that the discovery of Earth's interstellar sister is a question of years, not decades.